Greetings and welcome to a very special Man Bites COVID installment of QuantSlob titled What Flatten the Curve Isn't. Many of you may have seen graphs online or on television, like this really nice graph that shows the cumulative total of observed COVID infected cases, this one provided by the CDC, or the cosmetically different appearing, but otherwise essentially identical graph here provided by Bing. The term flatten the curve is used in a couple of different contexts. One involves the observed infected cases by time. The idea is that we want to avoid having too many infected cases at any one point in time so that medical services won't be overtaxed by those that need care. Another common use of the term flatten the curve comes from mathematical models epidemiologists use to describe the spread of a contagious disease. A very common and useful such model is the SIR model. Now, we're not going to offer a lot of detail about this here, but I've included links to some really nice videos that explain the SIR model in the video description below, and I encourage you to take a look if you're interested. In particular, the flatten the curve expression refers to the modeled number or proportion of infectives, people within the whole population who are contagious at some point in time. The purpose of this curve is to describe the rate of spread of the disease within the whole population. And to flatten basically means to level off the number of contagious people within the population. At the peak here, the modeled rate of new infected cases falls to 0, which is a very good thing. The important message here is that the paths or curves shown in the graphs we originally looked at are not the curves that are referred to in the expression flatten the curve. And the reason I wanted to point this out especially is because someone might, and they have, seen a graph like this and think to themselves that, well, this curve isn't flattening out at all. And then, they get depressed and discouraged, and that is not cool. These plots show the observed cumulative total of infected cases. Now, we can take our observed cumulative total curve and easily convert it into a plot that shows number of infected by day. And we do this, by the way, by diffing, short for differencing. And here we see that the trend appears quite different than that of our cumulative total. Another point here is that even this non-cumulative plot does not accurately convey the rate of spread within the population, not like the curve in the SIR model we just looked at. The reason, of course, is that these numbers are really a function of the number of people being tested and how and why they are being tested, and this is changing over time. To give an example, suppose one day we ask 10 people if they are basketball fans, and let's just say that 4 say that they are. The next day we ask 100 people, and 36 of them report that they are basketball fans, and the day after that we ask 1,000 people, and for the sake of example, let's say that 410 of them report that they're basketball fans, and the day after that, we ask 10,000 people, and just for the sake of example, let's say that 3,950 of them report that they are basketball fans, and you can see one might be left with the misimpression that basketball fanship is growing exponentially. And that's it. That's going to do it this time around. Thank you very much for tuning in. We are wishing all of you the very, very best. Don't forget to stay tuned for more QuantSlob.